about media, two different media where you get waves incident and then reflect from the media. So we're going to call this simply region 1. It doesn't matter what it is, in this region 2. Now, in general, we're talking about plane waves at a given frequency, constant frequency. So these medias have parameters. There'll be some sigma 1. Some, matter of fact, let's do it this way. Let's make that lossless so it doesn't cause any real problems. We're going to make this media just has some mu1 and some epsilon 1. This media can have some sigma 2, some mu2, and some epsilon 2. And we'll call this the x or the z direction, and let this barrier be the x coordinate, and we're going to have an electric field coming in incident here. It'll have some E, and it'll be some E naught, e to the minus j beta 1 z in the ax direction. Now that's just a plane wave coming normally incident into this boundary. Y'all follow me, class? Can you all see this okay? Now that's going to cause, because this is different types of media, one of the waves is going to actually reflect this way. And that's going to have a value of some E naught reflected, e to the minus j beta 1, or plus j beta 1 because it's going in a negative direction, and the ax orientation. That's the reflected wave. There'll also be a transmitted wave. So there's going to be some transmitted wave. And this E transmitted is going to have some E naught transmitted times e to the minus, and this is going to be minus j beta 2 times z, but it could have an e to the minus alpha 2 times z as well in the a's or ax direction. You all follow me? So I'm just showing you. Now we have waves, a wave coming in, expressed by this, and I might as well put an E0 sub I, then you have a reflected wave going back and a transmitted wave. Can you all follow me on this? This is simple. Now, they give rise to an H fields. We get the H fields by going ahead and so the H fields themselves, we always get using the standard relationship that H is equal to 1 over eta, unit vector in the direction of propagation crossed into the E field. That's for any type of fields, incident, reflected, or transmitted. All right, if we have the incident E field, we can calculate the eta, and then we can go ahead and get the H fields. Now, for this one, let's do the H field for the incident one first, all right? So H incident here would be, think about this, remember how it would always be a ratio of E naught incident over eta 1, if it's strict real. Y'all follow me on this? That's the magnitude of the H field. Then it's going to be times a unit vector in the direction of propagation. Well, I'll tell you what, let me do it. I'm going to change that for a second. Sorry. I should have said that first. I'll put it this way. It's 1 over eta 1. What's the unit vector in the direction of propagation for the incident wave class? You got to know this for the quiz for sure. Tell me, what is a unit vector in the direction of propagation for the incident wave? AZ, right. AZ. And then it's crossed into the E field. Now the E field is given by E naught incident. And it's times e to the minus j beta 1 z ax. So here I can see that the H field is going to have a magnitude of E naught incident over eta 1. Then I have e to the minus j beta 1 z, and it would be z crossed x is y, ay. Likewise, we can go ahead and get the H field for the transmitted wave. Now, I know, just because it should be pretty obvious to you, if the E field coming in incident going this way, I know E cross H is the direction of propagation, right? So E field cross H is direction of propagation. This one's propagating in the plus E direction, so E cross H has got to be in the Y direction, right? And we know the H field is going to be that way. If you don't, we could do it. For the transmitted H field, it's going to be 1 over, now this is going to be eta 2, and this has both a magnitude and a phase angle. I'll just call it the angle of beta 2 right here. Unit vector in the direction of propagation is AZ, and it's crossed into the E field, which is some E naught transmitted e to the minus j beta 2 times z, and possibly e to the minus alpha 2 times z as well in the AX direction. This will be rendered as H transmitted. Will simply be 1 over, or really it's going to be E naught transmitted over magnitude of eta 2. And then we have z cross x is AY, so make sure it's in the AY direction. And then it's going to be e to the minus j beta 2 times z, e to the minus alpha 2 times z. And then I'm going to take the phase angle upstairs, so it's going to be e to the minus j, and it's the angle associated with the impedance of that region. You all follow me on this? I'm just rewriting this, so that's the transmit. What about the reflected H field? Now that's in the first media, right? That has an impedance of 1 over eta 1. What's the unit vector in the direction of propagation for the reflected wave, class? Minus AZ, right? Got to make sure you get this right. So it's minus AZ, and it's going to be crossed in the reflected field. That's going to be E naught reflected times e to the plus j beta 1z, because it's going in the negative direction, and it has an AX component. So for this one, the reflected field has a magnitude of E naught reflected over eta 1, and there's a minus sign. Well, yeah, I'll leave it as minus right now. And then I have to have e to the plus j beta 1z here. And then I have AZ cross AX is positive AY, right? But there's a minus sign out here. So this has got a minus value there, and it's going to be AY. So those are the field components, both the H field and E field components for the incident reflected wave. This is spelled out in Dr. Wentworth's book very clearly. Okay. He has it. How many looked at in this book? Anybody? A couple people? It's as clear as a bell what I'm doing here. Yeah.
Why is the exponent for the E positive on the
Can anybody answer that? Why is the exponent e to the plus j beta 1z? Anyone? That's right. That's propagation in the negative z direction. If it was a minus j beta 1z, it would be going the positive z direction. Follow me, everyone? All right. So now what we have to do, and this is something you get used to doing over and over again in EMAG, especially for things like radar and that kind of design, you match the actual boundary conditions. The tangent E field on one side is equal to the tangent E field on the other. Do y'all remember that? E tan 1 is E tan 2. And the tangent magnetic field on one side is equal to the tangent magnetic field on the other. Now we, because we don't like to do a lot of extra work, we make this interface right here being at z equals 0. Y'all follow me? Now the reason I do that is when I look at the tangent E field on one side, the first media, I get E naught, right, incident, plus E naught reflected, just equal to E naught transmitted. The reason is all these beta terms are z equals 0, so e to the 0 is 1. Y'all follow me? That's the reason we select the boundary at z equals 0. So that's the E field. What about the H field? Well, the H field is H tan 1 is equal to H tan 2, right? Here you have to take care with the sign. Make sure. That's the E field. The H field, well, H incident is right there, and it's at z equals 0, so e to the 0 is just 1, so I got E naught incident over eta 1, but then for the reflected field, because both the reflected and incident field on region 1 on that side of the actual boundary, then I have minus E naught reflected over eta 1 is equal to E naught transmitted over eta 2. Y'all follow me on this? And again, I'm just taking the boundary conditions. Tangent H fields at the boundary are equated. There's 2 in region 1, 1 in region 2, the tangent E fields. Everybody follow me on this? So now we go ahead, and what we want to do is we want to get equations that have just the ratio of the transmitted to the incident or the reflected to the incident electric fields. These are called reflection or transmission coefficients. So to do that, I start, and I'm going to do it this way. If I just go ahead and replace E naught transmitted with this, I get E naught incident, right, plus E naught reflected over 82. Y'all see, I've just taken that and I've stuck it in there for E transmit. With me on this, everyone? Then the next thing I'm going to do is multiply everything by A to 1, A to 2. And in doing so, I take it back. What I'm going to do next, I thought about this, just to make my life even easier. When I look at this right here, now I'm going to divide everything by E naught incident. And I'm going to define a reflection coefficient. This is called reflection coefficient. As the ratio of E naught reflected to E naught incident. Okay. So now I divide everything by E naught incident. This becomes 1. Take a look at it. This is not a hard thing to do. This becomes the reflection coefficient. Right here. This becomes 1. And this becomes the reflection coefficient. With me? And I'm defining this. This is standard in electromagnetics. Reflection and transmission coefficients are used all the time. So now we have to solve for that. So now I multiply everything by A to 1 and A to 2. So I get A to 2 minus A to 2 times gamma is equal to A to 1 plus plus gamma times A to 1. Follow me? Nothing tricky at all. And now I'm going to rearrange this and solve for gamma. In doing so, you can see what happens. I take this to this side, and now I get quantity A to 2 plus A to 1 times gamma is equal to, and this is going to be A to 2 minus A to 1. Or finally, I can just write that the reflection coefficient itself is equal to A to 2 minus A to 1 over A to 2 plus A to 1. And of course, eta is equal to the square root of j omega mu over sigma plus j omega epsilon. So that's the reflection coefficient. Now, the transmission coefficient is the ratio of the transmitted field to the incident field. So the transmission coefficient, I'll put it over here. The symbol is just tau is equal to E naught transmitted over E naught incident. I can go through this same process, but I think some of you can realize this. If you just look here at this boundary, I know that I have E naught incident plus E naught reflected is E naught transmitted, right? E naught incident plus the reflection coefficient times E naught incident is equal to E naught transmitted, or E naught transmitted is equal to simply, or really tau here, is simply equal to 1 plus the reflection coefficient. Now tau can also be rendered this way. It's 2 times A to 2 over A to 2 plus A to 1. So this is the transmission and reflection coefficient for a standard normally incident wave where we're assuming the boundaries of t equals 0. Do y'all follow me on this, guys? Now this is really useful. If we wanted to get the power, and just tell me about this. If I wanted to get the power in the incident wave, how would you do it? What's the, if we assume it's lossless, let's do it that way. What is power, really? Power density, I'm sorry, power density. Technically, it's 1/2 the real part of E cross H conjugate, right? But if it's a lossless media, what happens? I mean, that's region 1. If it's lossless, this is one thing I try to instill in you guys, make sure you know this. If it's lossless, the average power density, right, is just equal to 1/2 magnitude of the electric field squared over eta, and it'll be propagating in the direction of propagation. Do y'all follow me? That's, how many remember that? All right? I mean, this should be, by this time, better. by this time, it should be more or less instilled in you. This is an assumed fact. When I teach this course, by this time, you gotta know this like the back of your hand. All right, if I know that's the power density, what is the power density in an incident wave? It's losses, right? So it's just what? 1/2 the magnitude of the incident field, right, squared, over eta1, and it would be, in this case, in the AZ direction. This would be watts per meter squared. Y'all agree with that? What about the power density in the reflected wave? We know it's going in the opposite direction, right? Do you all agree with that? What about the magnitude? Well, the magnitude is whatever the E field reflected is squared, right? We need to do that. So the reflected field is simply reflection coefficient times the incident field, or you can see that P, the average power, in the reflected wave is going to be simply 1/2, and then replace the reflected field value with its E naught incident reflection coefficient, or you can take it times simply magnitude of E naught incident squared times magnitude of reflection coefficient squared over eta in region 1, but there's a caveat here. You gotta have a minus sign or something that indicates the thing's propagating the other direction, and then AZ. And that would be watts per meter squared. Now, the final thing is, that's the reflected power, that's the incident power. If we go ahead and get the transmitted power, we can do it two ways. We can just say incident power density minus reflected power density is the transmitted power density. That should make logical sense to everybody. You all with me? Or you can go ahead and say the transmitted power density is simply going to be 1/2, and then you can take the magnitude, and I'll leave tau times E naught incident in here, in square, divided by magnitude of eta2 right here. Now, because that could be lossy, you also have to take cosine of theta in region 2, of the angle associated with the impedance in region 2, and it would be in the AZ direction. So that, in a nutshell, is how you get the reflection transmission coefficient and the power densities associated with each. A good thing to do here is do a simple example so you can appreciate this. It's not hard, and it exactly parallels what you've done in transmission lines. Y'all remember with transmission lines? You had reflection coefficients and you had transmission coefficients, right? And it was a pretty straightforward process. This is the exact parallel for the electric field instead of just voltage. And I might as well add one other thing. Well, you could say that the incident field itself was equal to E naught, E field in region 1. The total field in region 1 was E naught incident, and then it would be times E to the minus J beta 1Z plus the reflection coefficient times E to the plus J beta 1Z. Do you all follow me on this? That should look very similar to what happens for the voltage on a transmission line, right? Except instead of V, I'm using E. It's electric field. And you could go ahead and get the H field in region 1, and that would be E naught incident over eta 1, and it would be times E to the minus J beta 1Z, but it would be minus the reflection coefficient E to the J beta 1Z, and this would be AY. I'm sorry, this would be AX on that, AX. That would be AY. You all agree with this, class? And I've just condensed them now. I mean, I'll put them in, and for the transmitted field, you don't need to do this really because you only have one component. Okay? So let's do a simple example, make sure everybody understands it. So, this is the kind of stuff I would give on a quiz. If I had two regions, region 1, and let that be air, and this region has, say, epsilon relative equal to 9, mu relative equal to 1, and sigma equals 0. So I say I have an electric field coming in, and the electric field has an amplitude of 10 volts per meter. Now, both regions are lossless. Do you all agree with that? Sigma is 0, it's lossless. So I want to know, first of all, the magnitude of the reflected field, just the magnitude. I want to know the magnitude of the transmitted field, just the magnitude. And I want to know the magnitude of the H field transmitted, just the magnitude of it. So you can put it like that if you want. And I want to know the actual power transmitted, the average power density transmitted, and just the magnitude. So let's go through it. How do you do this one? Anyway. Well, normally the first thing you have to get is eta, right? Because everything is based on the values of the intrinsic impedance in the two regions. So for air, what is the value of eta, anyone? It's really eta naught or 120 pi ohms, right? Over here, what is it going to be? Sigma 0, right? So I don't need to worry about that j omega mu over sigma plus j omega epsilon. What I can do is get what? Eta, in this case, because it's lossless, is square root of mu over epsilon. You all agree with me? So I can say it's a square root of mu naught over epsilon naught, right? And then I can take it and multiply it by square root of mu relative over epsilon relative. Well, square root of mu naught over epsilon naught is? It's 120 pi ohms. And mu relative is 1, so it's 1 over the square root of epsilon relative. 1 over the square root of 9 is? 1 over 3, right. Divide by 3. Or this one is 41 pi ohms. You all agree with me? Now, after that, how do I get the reflection coefficient? We just did it. Reflection coefficient, this is the way I like to teach people this. It's the same thing that it was back in the day when you did transmission lines. It's the impedance you're going into minus the impedance you came from in terms of characteristic impedance divided by the sum. So the impedance I'm going into is 40 pi. Right? The impedance I came from is 120 pi. And the sum of those is 160 pi. You agree with me? So what's that going to be? Well, I got 40 minus 120 is minus 80 over 160 is minus 1 half. Minus 1 half. What is the transmission coefficient? Well, it's 1 plus the reflection coefficient, or it's 1 half, isn't it? Y'all agree with me now? Can you all see this, class? All right, now, the thing I asked for is the magnitude of the reflected field. What's that going to be? Just look at it. It's simply going to be the incident field strength, 10 volts per meter, times 1 half, or 5 volts per meter, correct? And actually, the reflection coefficient is negative, so if you want to be exact about it, be minus 5 volts per meter. Do you all agree with me? Technically, I asked for magnitude, so it's really 5 volts per meter. Over here, the reflected field's magnitude is 5 volts per meter. If I wanted the exact value, it'd be minus 5 at the surface. What about the transmitted field's value over here, class? It's just 5 volts, right? Same as the reflected. You all agree with this? So this is 5 volts per meter. Now, be careful here. What is the transmitted H field? Magnitude. Well, it's what? It's the E field divided by eta in that region. The E field is 5, correct, guys? Y'all with me on this? 5. That's what we calculated, right? So this is going to be 5 volts per meter divided by eta 2. What is eta 2? 45. So that would be, whatever that is, in amps per meter. Agree? This is a good little problem, right? It showcases everything you need to know, but didn't know who to ask. All right, so then what happens to the average power transmitted? What is that going to be? Well, it's lossless, right? Yeah, and we got to make sure we get the right values here. You're absolutely right. The average power is going to be 1 half. It's lossless, so I can do this. I can take the magnitude of the transmitted E field and square it and divide by eta 2, right? Eta 2 is 40 pi. Now, the transmitted E field was 5 volts per meter, right? So it's 5 squared is 25, so it's gonna be, let's see, 25 by 2 divided by 40 pi, and I'm not sure what that is, but I think you get the gist of what's going on here. One thing you're gonna find, if we do this right, if I went and got the incident power density and subtracted the reflected power density, I'll get this value. Or I could just do it this way. Y'all follow me? They'll always give you the same answers. Any questions about this? Because this showcases normal reflection, normally incidence wave reflection, as easy as it gets. Y'all follow me on this? And it's no harm. The only thing that's a little more difficult, if this media is now lossy, then when you get the power over here, you're going to have to take into account, and I think I erased it, the cosine of that angle, all right? And you have to divide by the magnitude of eta and the cosine of the angle transmitted, or the characteristic impedance of that region's angle. Okay, next.
I have a question. Since the reflection coefficient gamma, because it's negative, that means that the reflected wave is actually pointing down.
At this point, what happens is, the electric field at this point, if we're talking about the phasor domain, this is positive, the reflected field's negative to start with. The sum of those two, 10 minus 5 is 5, the transmitted field is 5, but it would start negative here if you want to be exact about it. At this point, most of the time the work I do, unless you're doing mathematical derivations, the only thing they care about is the actual magnitude. That's what they measure. And that's the one thing you have to understand. Okay. So that's, I don't know if I want to get into this, but I'm going to dabble with this one. So that's normal incidence. Now, what happens if we have waves coming in oblique incidence? Normal incidence is like a wave's coming in, normal to the surface. Oblique would be a wave coming like this, hitting, not hitting normal, at an odd angle, something less than 90 degrees. Follow me? So we'll talk about this, and we're going to start with a mode called TE mode. But this gets a little mathematically rigorous, but it isn't bad. So in your book, I don't have my book here, but I'm not sure what page it's on, but if you look, you'll see near the end of chapter 6, oblique incidence. You guys have your books here somewhere? There you go. And the first thing when we talk about oblique incidence will be the TE wave, TE mode. That's transverse electric. So, I'm going to stay consistent with with his nomenclature and actually his coordinate system. So, what he does is he has two regions. This is going to be the z direction. This is region 1, and this is region 2. Now, Dr. Whitworth's book, he does this only for a lossless cases. So he's assuming sigma in both regions is going to be 0. You all with me? So when he does this, he's going to say, I'm going to assume I have an electromagnetic field that's going to be propagating this way. Now, put it this way. I have an electromagnetic field, but the field is out of the board. This is X and Y is out of the board. So I'm assuming this is the electric field. It's out of the board, and it's the incident wave, and it's propagating this way. Now, that vector, that direction of propagation, the unit vector and direction of propagation, has both Z and X components. Do y'all see that? It's not going in Z, it's not going in X, it's going in combination. But I need that. When this wave hits here, some of it is reflected, and I'm going to have a reflected field. I'll call it E reflected. And I'll write the equations for these, and I'll also have a transmitted field. Now, this is called the angle of incidence. This is the angle of reflection, and this will be the angle of transmission. You'll notice it's being measured from the normal. With me on this? If that angle was 0, it would be normally incident. y'all follow me? But here we've got some offset, so wave comes in, goes there, and this would be the transmitted electric field here. So the equations for these are a little interesting. I want you to just bear with me. For the incident field, it's going to have a magnitude. Now, I got to tell you this. The reason it's called TE, and please listen, this is important. It's transverse electric. In the plane that it's propagating, the E field is perpendicular. Y'all see that? That's called a TE mode. The electric field is perpendicular to the direction of propagation and to the plane it's traveling in. Now, something that gets a little confusing is when it hits this boundary, do you see how the entire field is parallel, or it's actually tangent to the boundary on both sides? Y'all see that? That'll help us in the analysis. That's called a TE mode. A TM mode would be with the electric field in the plane of the board. The E field would look like this, and the H field would be perpendicular. All right? That's called a TM, or transverse magnetic. The magnetic field now is perpendicular. But we're talking about the TE mode only. So if I come over here and I write the equation, I get this, and I get e to the minus j, and this is going to be beta in region 1, but it's going to have a z hat, and I'll explain that in a second. And it would be in the AY direction. Now here, y is sticking out of the board, so the E field is sticking out of the board. It's in the AY direction. Y'all with me? This gets interesting. The z value here is actually equal to z times the cosine of theta incident plus x times the sine of theta incident. And I'll try to explain this. He does this in the books. But if you just think for a second, if you have something where I have a given z value here, let me do it this way, a given z value here, and you look at this, or call it, I'm sorry, z hat, call this z hat. Now just understand, I'm trying to show you a distance here, and there's an angle right here, theta incident, and you can see that I'm trying to do this in a way that's meaningful. This is z and this is x. If I take z times the cosine of that angle, right there, I get this distance. And if I take x times the sine of that angle, I get this distance. So if this is x, take the sine of that angle times x, I'm going to get this component. It's opposite over adjacent, or opposite over hypotenuse. And if I take this and take the cosine of that angle, I get this distance. What it boils down to is that is what this coordinate will be. So now I'm going to write E field. You'll have to look at this for a while to really appreciate it. It's going to be some E naught incident, and it's going to be E to the minus j beta 1, and then it's going to be z cosine of theta incident plus x times the sine of theta incident, and it's in the AY direction. I gotta say something else about this. I know this is it's hard sometimes to get a handle on this, but appreciate it. Take a good look at it and just play around with it. It works. As a matter of fact, if you look at this equation, when theta is 0, you get z times cosine of 0 is 1 plus 0, so you get normal incidence then. Y'all follow me?
So is that just the unit vector in the direction of propagation?
Now, this is nothing to do with the unit vector, right? That is an actual measured value. That is in propagating, it's propagating in space. So this would be equivalent to like the normal z component. It's propagating this way. A unit vector, since you brought it up, a unit vector in the direction of propagation will just be cosine of theta incident AZ plus sine of theta incident AX. And you can check that. Let the angle theta go to 0, right? So it's normally incident. Cosine of 0 is 1. Sine of 0 is 0. It's in the AZ direction. It checks. If it's coming in at 90 degrees, if all of a sudden this angle is 90 degrees and it's coming up here, well then the cosine is 0, but the sine of 90 is 1. It's going in the AX direction. You all see that? That unit vector just tells you what direction it's propagating. So that's the direction of propagation for the incident field. Now, if we wanted the magnetic field of the incident wave, what would it be? they're plane waves, remember that. So how do we always get the magnetic field? We say H incident would be equal to 1 over eta 1, right? Unit vector in the direction of propagation, this guy. So it's going to be cosine of theta incident AZ plus sine of theta incident in this case AX, and that has got to be crossed into the electric field, which is E naught incident e to the minus j beta 1, and then it's z times the cosine of theta incident plus x times the sine of theta incident in the AY direction. Y'all follow me on this? I'm only taking the values, the stated values, and I'm putting it into that 1 over eta unit vector and direction of propagation crossed into the E field. Y'all follow me? This is just a standard way. It's simple to see what's going on if you think about it. Now I've got to go do the cross products. And what happens? I can see my H incident have a magnitude, as before, E naught incident over eta 1. Then I have to do this cross stuff. So I have AZ crossed AY is minus AX, right? So that means the first term is going to be minus cosine theta incident AX, and then I have AX crossed AY, which is positive AZ, right? So it's going to be plus the sine of theta incident AZ, and then you'll have the e to the minus j beta 1, and it would be z cosine of theta incident plus x times the sine of theta incident. And that would be the vector. Does anybody have their book open to this? This would be the incident H field for the TE mode. Can you see it?
I've got it right here.
It's the bottom of page 361, and you'll have incident E field and incident H field. Y'all see it? How many have their books here? If you look in your books, you should be able to see it. I mean, you don't have to, but it's at the bottom there. All right, so that's the incident H field and the incident E field. If we wanted to get the transmitted E field and transmitted H field in the same way, by the way, they'll have the same basic shape. If you take a look at this, the transmitted field, E naught transmitted, E naught transmitted, like that, E transmitted, going to have a magnitude, E naught transmitted here. It's going to be going in the minus j here, it's beta 2, then it's going to be z times the cosine of theta transmitted, right, or theta 2 if you want, plus x times the sine of theta transmitted, that's that angle. It's going to be in the AY direction. Now the unit vector for this one, just like the other one, the unit vector in direction of propagation will be cosine of theta transmitted AZ plus sine of theta transmitted AX. So same exact thing, only now the angle changes. This is the transmitted angle, that was the actual incident angle. Y'all follow me? That's the only difference. So if I get the H field transmitted, anybody want to take a guess what's going to happen? That one's coming in like this one's moving like that. It's going to have the exact same form as this one, this hear me, only now it's E naught transmitted. This is eta 2, right, not eta 1. And then this is going to be minus the cosine of theta transmitted plus the sine of theta transmitted. Y'all follow me? It's going to be the same thing, only the values will scale differently.
Well, the directions will be the same too.
Well, not exactly the same. See, this one's coming in like this one's like this. That's why that cosine of theta transmitted would be different than cosine of theta incident. So the
Will the signs all be the same then?
The signs are, that's the thing. So over here, what do I get? If you look at that for the transmitted field, for transmitted H field, now I get E naught transmitted, right, over eta 2, right? Now I get minus cosine of theta transmitted, and you can take a look, that's AX, plus the sine of theta transmitted AZ, right? Let me go ahead and erase some of this. Right here. Then it's gonna be times e to the minus j beta 2 times z cosine of theta transmitted plus x sine of theta transmitted. And that's it. And it would be amps per meter. That's the transmitted H field. Now, after that, you need the reflected E field and reflected H field. You're looking at books, he's a lot neater than I am, right? But he'll clear up any kind of thing that you don't quite see. But for the reflected field, now pay attention to this one, this is important. It's gonna have a value of some scalar property, E naught reflected. Then it's gonna be E, and it's gonna be to the plus J, not minus beta 1, and it will be Z cosine of theta incident, or cosine theta reflected. You'll see in a second that theta incident and theta reflected are the same. And then it's gonna be minus X times the sine of theta reflected. And this will be in the Y direction. Now he shows that, you have your book, right? And if you look, right here, right there, see the reflected field? And actually he leaves it as minus J beta, but right here, see that? That's the same thing, it's equation 6.121. Tell you the truth, I'm gonna have to give you a quiz now, because I'm gonna run out of time, but so here's the deal, class. I'll give you some things to do with this, for reading some, and please do that. So. Alright, everything off your desk, and first thing you do, and then this row gets